Hi everyone, Lily here. This is the second quarter update for Science and Force Fields at OpenFF. A bit of a shorter one than Q1, as most of the team spent a lot of time variously preparing for and attending the May OMSF workshop, attending other conferences, or often PTO, sick, or parental leave. That said, we've still managed to make a fair bit of progress on our general roadmap deliverables, so without further ado, let's get into it. Last time, we talked a lot about our water model co-optimization project and the various updates we had made to software and data workflows. Broadly, this can still be divided into three major directions. Firstly, fitting a three-site MVP using force balance, troubleshooting particular alcohol and amine properties, and creating a new DimSim library for future optimizations using a new PyTorch-based architecture. The MVP part of this is still in progress. Unfortunately, progress has been a bit slower on this than we would like, partly due to our GPU compute needs starting to conflict with other major projects that we've been working on. So we are still pre-calibrating our expanded public dataset using Sage 2.3. However, Chris has started benchmarking and optimization simulation performance on Frontier, so this bottleneck will hopefully relax soon. We are also still working on discussions with NIST to release an expanded dataset with more properties that we can train and validate too. Chris has also been looking more at particular subsets of properties that perform poorly, focusing initially on alcohol and water mixtures, particularly on enthalpies of mixing. We think that this may be an electrostatics issue, and previous work has found that rescaling alcohol charges substantially improved alcohol properties. So working off a base of our AskGC charges, Chris has been performing grid searches over scaling factors and identified a set of values that perform well for simple alcohols. He's now evaluating the transferability of these scaling factors to mixtures of alcohols and diols, and is starting to look into whether optimizing the van der Waals parameters with the new charges will give further improvement. Once we've settled on a good set of parameters, we will need to work out how to best fold this into our existing charge model, whether we can do this as a post-processing step or independent step, or whether we'll need to integrate this into AskGC itself. Lastly, Matt has continued working on developing a new library for compute management so that we can move on from force balance and co-optimize valence and van der Waals terms using a PyTorch-based approach. This library can be best thought of as a replacement for OpenFF Evaluator, and over the past couple of months, he's ported over existing functionality for handling ThermoML datasets and started working on scaling up the approach prototyped in the Descent library to apply to production-level fits. This has meant both extending the property types already implemented in Descent, as well as experimenting with and converging on an approach to compute management with prototyping on natural clusters. Last but not least, we have a couple of other updates. So firstly, since last quarter, we've made a new release of Descent, version 0.6, that adds support for regularization during training and adds support for periodic systems when calculating energies. We've also tried to make Descent more user-friendly by adding more documentation. Secondly, just highlighting that Danny and Finlay have released Presto as a mature product with a preprint on ChemArchive. So please do check it out if you're interested. This is a bespoke fitting workflow that uses SME and Descent to train force field terms to MLP data. Moving on to Sage 2.4 work, this is fairly short, but we have been looking at the recently released dataset from ByteDance. So this dataset, also called TheML, contains optimized geometries, torsion scans, and Hessian data at our level of theory, and is orders of magnitude larger than what we have in QCArchive. So it seems like a very promising source for additional training and benchmarking data. We have already begun using it in some protein force field fits, which I'll talk about later, but I've also started looking at whether it can inform future Sage fits as well. For example, we've identified a number of parameters that have bimodal or multimodal distributions of predicted equilibrium values, suggesting that they may benefit from being split to be more specific as to which chemistries they cover. We're still in the progress of looking through the dataset and planning the next Sage 2.4 refit. In terms of key next steps, we also want to augment our existing benchmark sets to increase coverage of sparse chemistries and ensure all our parameters are covered. All right, on to the protein force field project. Just to recap, we started this project several years ago with the goal of co-optimizing parameters to small molecule and protein data for a combined force field that performs well on both small molecules and proteins. And this is being led and driven by Chapin and Cavada from the Gilson lab. As an initial target, we're aiming for similar accuracy and performance to existing protein force fields, as benchmarked across 4 tiers of benchmarks that increase in computational expense and structural diversity. What we have tended to find is that with our force field candidates, we do quite well on tier 1 benchmarks, which include QM targets and scalar couplings of short unstructured peptides. But our candidates have difficulty with benchmark targets that assess secondary structure, such as keeping proteins folded in long timescale simulations. Last year, we released a rosemary alpha force field that was fit to small molecule and peptide QM data, as well as to the GB3 and helical peptide targets, or the tier 2 benchmarks. On benchmarks, rosemary alpha achieved good performance on most of the targets in tier 2, although performance on head egg white lysozyme was still worse than AMPA14SB. Last quarter, we analyzed tier 3 benchmarks that indicated this was a general force field problem, but further refitting to hen egg white lysozyme targets didn't improve general performance. In addition, we did some small molecule benchmarking and found that rosemary alpha introduced some pathologies, mostly around sulfur, phosphorus, and carboxylate chemistries. We did decide to move rosemary alpha to release as a peptide force field once we fixed these, while continuing to work on folded protein behavior. But Chapin found that doing a normal small molecule and peptide QM refit from rosemary alpha degraded performance on tier 2 benchmarks, even when he froze the 6 specific protein torsions that you tune to the tier 2 targets. So instead, we decided to move forward in 2 parallel efforts. Over this quarter, Chapin looked at the easiest path forward, which was just to patch the problematic parameters in rosemary alpha to the stage 2.1 values without a refit. This is the smallest modification we can make to rosemary alpha, so it is the most likely to keep performance on proteins where it currently is. In parallel, OpenFF would move along this pathway, where we would take the rosemary alpha and integrate it with stage 2.3 typing. We will refit valence parameters while perturbing torsions as little as possible, and if this retains protein performance, release that as rosemary 3.1. Oops. Both paths are still in progress, but here is the current status. In path 1, which is just patching the problematic parameters, Chapin identified 8 bonds and 2 angles as the key targets to fix. He made a new force field called rosemary alpha 1b, where these are patched back to the stage 2.1 values. This force field successfully fixes the large errors in problematic parameters, while keeping the same performance on overall QM metrics as stage 2.1. Next, he benchmarked this force field on rosemary targets. On tier 1 targets, this force field performs very similarly to the original rosemary alpha. On tier 2, however, we see some differences. Firstly, rosemary alpha 1b results in higher helicity on the AAQ-AA3 benchmark than rosemary alpha. In this particular benchmark, none of the parameters changed affected these simulations, so this is wholly due to sampling differences between the replicates. Secondly, rosemary alpha 1b unfolds the GB3 alpha helix and has higher error on NMR observables than rosemary alpha. For GB3, there was one parameter that changed between rosemary alpha and rosemary alpha 1b, but this is just a minor modification of a carboxylate bond. So we're still trying to work out if this is a meaningful difference or more differences in sampling. In terms of next steps, we're focusing on benchmarking this force field more. We will proceed with the tier 3 benchmarks of rosemary alpha 1b, starting with protein ligand binding for energies. We will also run an additional 3 replicates each of rosemary alpha and rosemary alpha 1b on the GB3 target to further characterize differences between the performance on the 2 force fields. For the second path, this involves a greater change to the force field, so we did some more experimentation. Our first step was to retype parameters from stage 2.1 to use the stage 2.3 partitioning, although we left the van der Waals parameter values untouched to retain protein behavior. We then investigated the impact of a number of variables. The first was data, which dataset we use for deriving initial bond and angle values via the modified Seminario method, as well as which datasets we use for training. Secondly, torsional flexibility, whether we completely froze all torsions or refit them using prior widths of 0.1, 1, or 5 kilocalories per mole. Lastly, we also experimented with different weightings between training targets. In general, we found that the combination of variables that gave us the best performance was to use initial values calculated from the larger ByteDance or Themol dataset, and to train to a combination of QC archive and Themol data. In addition, using the default weighting of the different training targets gave us the best results. We did observe that freezing torsions resulted in worse performance on bonds than allowing them to optimize, so we are still experimenting with allowing torsions to optimize with a narrow prior. We have found that using a prior width of 1 kilocalorie per mole is enough to improve performance on bonds, and tier 2 benchmarks are still ongoing to see if this will negatively impact folded protein performance. Lastly, Ashley is still continuing work on benchmarking the rosemary alpha force field on cyclic peptides. This quarter, the simulations have completed and she has started analyzing the results, which we'll hopefully present next quarter. Onto lipid, there have been a few updates here. As a reminder, this project is being driven by Julianne from the Schertz lab, and the goals are fairly similar to the protein force field. Getting parameters that perform well on both small molecules and membranes, and a force field that performs in line with existing membrane force fields. As a means of measuring performance, Julianne has two sets of benchmarks that she is using to compare performance. The first is alkane benchmarks, such as torsion energetic profiles, physical properties, and trans-Gauss ratios. The second incorporates actual membranes and measures common targets such as area per lipid, bilayer thickness, order parameters, form factors, and she's also been looking at relaxation time. As with the protein force field, I'll just quickly summarize where we were at the start of the quarter. So on benchmarks of previous stage force fields, primarily stage 2.2, Julianne found that they performed in line with other lipid force fields on metrics like area per lipid and bilayer thickness. However, they performed pretty badly on order parameter quality and were quite slow to relax. She tried a number of different refits and found that retraining to a combined small molecule and lipid dataset didn't shift the torsion terms for alkane profiles, which, as you can see here, get the relative energies of the trans and Gauss conformers pretty incorrect. Retraining to an alkane-only dataset improved this particular target, but actually matching the QM profile exactly resulted in overestimating the trans-Gauss ratio in simulation. She also ran into repeated issues with training phosphate parameters to QM, which may be because the constraint optimizations that we use during training with force balance result in very different conformers when optimized with relative to QM. The workflow that she saw the most success on was to retrain valence terms to an alkane QM dataset and then retrain van der Waals parameters to a combined alkane and methyl acetate physical property dataset. This improved order parameters, although not to the same extent as other lipid force fields. This quarter, following the full release of Sage 2.3, she reran her workflow and benchmarks using Sage 2.3 as a starting point. Interestingly, Sage 2.3 by itself already improves massively on Sage 2.2 with order parameters, and is now performing similarly to other lipid force fields like CHARM. Form factor quality is still low, though, suggesting possible issues with head group parameters, and the relaxation time is still pretty high. Retraining to alkane data from Sage 2.3 and porting the refitted van der Waals terms from the Sage 2.2 fit got the Sage 2.3 valence 1 force field. This improves relaxation time, but decreases form factor quality. Interestingly, this force field also decreases performance on general physical properties, especially halogenated alkanes. Julianne also tried refitting phosphate parameters using the Presto library from the Cole group, which was a lot more successful in matching QM profiles than force balance workflows. That being said, performance on lipid benchmarks didn't really shift substantially using these new terms, including in areas of concern. In terms of next steps, Julianne will keep benchmarking her refit force field on a wider set of lipid properties. To address some of the issues with overfitting to QM and physical property performance, she's planning to try co-optimizing valence of van der Waals parameters, as well as increasing the size of the training sets for her fits. Lastly, onto QM datasets and collaborations, both of which are being masterminded by Jennifer Clark. Over the past quarter, we have added a few more datasets to the QC archive. This includes a subset of molecules from SPICE2 that we identified as problematic for various reasons, such as overlapping atoms. This is only about 2,300 conformers, but we thought it would be useful to fix for force field training and validation workflows. We also added a small dataset covering PEG fragments as part of a training tutorial for fitting a force field for polymers. And lastly, the initial architecture dataset for diverse organometallic ligand complex structures has completed, and Jen is in the process of setting up a larger one for the ongoing Genentech and Cadera Lab collaboration. Speaking of collaborations, OpenFF has been collaborating with OpenFE to build a standardized benchmarks repo. I mentioned this last time as well, but just as a reminder, this repo supports relative binding for energies and absolute solvation for energies. It includes code for discovering available benchmark sets and includes standardized sets of partial charges to avoid charge variation affecting results. The repo also allows both building new networks and using previously generated ones, and includes comprehensive examples. We're pretty excited about this project as it'll make it much easier for OpenFF to run our own benchmarks in the future. And indeed, Jen is actually the one who is going to be running the Tier 3 RBFEs for the Protein Force Field project. At this point, this collaboration is largely complete. There are still some odds and ends to wrap up, but most of the minimum goals have been hit. Our main focuses for the next quarter are to continue with our ongoing work, focusing on the water model refit, getting the Rosemary Alpha closer to release, and continuing collaborations. We will also keep working towards stage 2.4 and helping with development of a lipid force field. So we'll hopefully update on this project next quarter. See you next time.